We often look up and see aircraft flying, but keeping them safe and airworthy involve a huge amount of work on the ground.
Absolutely. Constant, really meticulous work.
And right at the heart of that, maybe surprisingly, are some pretty basic hand tools.
That's right, the fundamentals.
So today we're going to get into these unsung heroes, really. The hand tools and measuring devices that aviation maintenance technicians, AMTs, use constantly.
And understanding these basics, it really gives you a new appreciation for how these complex machines are maintained.
Yeah, a deeper understanding of the safety and the processes involved. We've looked into the essentials, and we'll walk through them, explaining what they are, how they're used properly, and the safety aspects, too.
Exactly. We'll go through the categories, starting with the general purpose tools. Ready to jump into the toolkit.
Let's do it. Okay, first up, hammers and mallets. Seems straightforward, but there are nuances, right? Like metal head hammers being sized just by head weight.
Yeah, excluding the handle weight. It's specific. And then you have your soft-faced hammers.
With surfaces like wood, brass, lead, rawhide, rubber, plastic.
Right. And their purpose is key forming soft metals, working on delicate surfaces without leaving marks.
And you definitely wouldn't use them on, say, a punch or a nail.
No, absolutely not. You'd ruin the soft face pretty quickly.
Makes sense. And mallets, often hickory, rawhide, or rubber.
Good for shaping thinner metal where you don't want sharp creases. Think gentle persuasion.
And wooden mallets specifically for wood chisels or gouges.
Exactly. Always match the tool. General use is key, too. Pick the right one, make sure the handle's tight, really secure.
And the swing forearm and elbow hitting squarely.
Squarely with the full face. And safety glasses, always, if you're hitting metal on metal.
Good point. Keeping the faces smooth is important, too, right? To avoid damaging the workpiece.
Essential. Any damage on the face can transfer to the material.
Okay, let's move to screwdrivers. Everyone uses them, but aviation has specific needs, classified by shape, blade type, length, but basically for screws.
Loosening and tightening screws or screw head bolts. That's their job.
For the common flat blade, the advice is to use the largest that fits at least 75% of the slot. Why is that so critical?
Because if it's too small, it'll cam out, damage the slot, maybe even the surrounding part. You really want maximum contact.
Makes sense. You mentioned cam lock fasteners on cowlings.
Yeah, those are common. Quarter-turn fasteners, often seen on aircraft panels, and a good-fitting flat blade is needed there.
Okay. Now, recess heads Phillips and Reed imprints. They look similar.
But they're definitely not interchangeable. That's crucial.
What's the visual difference again?
Reed imprints has a perfect cross shape, comes to a sharp point. The screwdriver tip is pointed.
Okay.
Phillips has a slightly larger center in the cross. It's slightly rounded, and the screwdriver tip is blunt.
I'm using the wrong one.
Damages both the screw head and the screwdriver tip. You just won't get a good grip, and you'll likely strip it.
Got it. So always match them up. The most common Phillips are #1 and #2.
Yeah, covering screws from size 2 up to 9, pretty much.
What about offset screwdrivers or tight spots?
Exactly. Bent at 90 degrees on both ends. Great when you don't have much headroom. There are ratcheting versions, too. Very handy.
And some key safety points for screwdrivers.
Absolutely. Never, ever use one as a chisel or a pry bar. They're not made for that force.
They'll just snap, right?
Or you could injure yourself. And definitely don't use them to test electrical circuits. Big shock hazard.
Good reminder.
Yeah.
And secure small parts. Don't hold them in your hand.
Right. Put them in a vise or on the bench. If the screwdriver slips, you don't want your hand in the way.
We also saw those replaceable tip ones like 10-in-1. Economical.
Yeah, versatile. Flat, Phillips, Reed imprints, Torx, square drive tips, all in one handle, save space.
And cordless power screwdrivers. They seem common now.
Very common. They've largely replaced the old spiral ratchet types for driving multiple screws, but there's a big caution for aviation work.
Which is?
The slip clutch setting. You have got to set it correctly. Too high, and you can easily damage the screw head, over-tighten it, or even strip the threads.
So start screws by hand first.
Always best practice. Prevents cross-threading. And, interestingly, you generally shouldn't use a standard cordless drill with screwdriver tips for installing screws.
Why not?
They often lack that precise slip clutch. You can apply way too much torque without realizing it. Power screwdrivers are designed for that control.
That's a really important distinction. Okay, let's talk pliers. Diagonal, needle nose, duckbill, or common.
Yeah, those are staples. Their size usually just refers to the overall length.
What about round nose pliers?
Good for crimping metal, forming loops in wire, but they're not for heavy work. The jaws can spring apart quite easily. Sometimes technicians wrap the jaws to avoid scarring surfaces.
And needle nose, long, thin jaws.
Exactly. Half-round jaws, different lengths, perfect for holding small parts, adjusting things in tight spaces where your fingers can't reach.
Duckbill pliers, they sound specific. Thin, flat jaws.
Very specific. Their main use, almost exclusively in aviation, is for twisting safety wire.
Ah, safety wiring. Crucial stuff.
Absolutely. Prevents fasteners loosening from vibration. Duckbills give you the right grip for that.
And diagonal pliers, often called dikes.
Yep. Short-jawed cutters with the blades set at an angle. Great for cutting wire, small screws, rivets, cotter pins, and snipping off excess safety wire.
Key rules for using pliers.
2 big ones. 1, don't push them beyond their limits, especially the long nose types. They can be delicate.
And the second.
Never, ever use pliers to turn nuts or bolts.
Why not? People do it all the time at home.
Maybe at home, but not on aircraft. They grip poorly on the flats and will round off the corners of the nut or bolt head incredibly fast. Then you can't get a wrench on it properly. Use the right wrench.
Got it. Pliers are for gripping, bending, cutting, not turning fasteners. Okay, moving on to punches. Lots of uses here.
Definitely. Locating centers for drilling, starting the drill bit, punching holes in thin sheet metal sometimes, transferring hole locations.
And removing damaged rivets or pins.
Exactly. Solid and hollow types. Solid ones are classified by their point shape.
Like prick punches.
Right. Used for making small, precise reference marks on metal, maybe from a paper pattern. You only use light taps. Heavy blows can bend the punch or make too big a mark.
And center punches.
They make a larger indentation. The main purpose is to create a guide for the tip of a drill bit so it doesn't wander when you start drilling. Heavier body, usually a 60-degree point.
But again, not too hard to hit.
Right. You don't want to dimple the material excessively or push the metal through the other side, just enough to seat the drill.
Okay, so prick for marking, center for drilling. What about drive punches?
Also called taper punches. They have a flat face and, as the name suggests, a slight taper to the body. They're used to start driving out damaged rivets, pins, or bolts that might be stuck or binding in a hole.
And pin punches. Similar but straight.
Yes, sometimes called drift punches. Straight shank, flat face, sized by the face diameter.
So you'd use a drive punch first, then a pin punch.
That's the standard technique. Start it moving with the drive punch until the tapered sides touch the hole, then use the correctly sized pin punch to push it all the way out.
What if it's really stubborn?
A useful trick is to place a piece of softer scrap metal, like copper, brass, or aluminum, against the pin and strike that. It cushions the blow and can help jar it loose without damaging the surrounding structure.
Good tip. And a crucial don't.
Never use a prick or center punch to try and remove something from a hole. Their pointed shape will just wedge it in tighter, potentially expanding the fastener and making it harder to remove.
Right, tool for the job again. Lastly, for punches, transfer punches.
Yes. These are about 4 inches long, usually. They have a specific shape, a tapered point that then becomes a straight cylindrical section.
What's that for?
It's designed to fit perfectly into existing holes in a template or pattern. You use them to accurately transfer the exact center location of those holes onto the material you're about to drill. Very precise.
Okay, that covers the general purpose tools really well. Let's shift gears to wrenches, another huge category.
Absolutely massive. In aircraft work, you see open-end, box-end, socket, adjustable ratcheting types, plus loads of special ones. And Allen wrenches, of course, for hex socket screws.
Material matters here too, right? Chrome vanadium steel.
Very common. It's strong, durable, resists corrosion well. Good stuff for tools taking a lot of torque.
Let's break down the types. Open-end wrenches.
Solid, non-adjustable. They have parallel jaws, usually offset at a 15-degree angle to the handle.
Why the angle?
It allows you to get more rotation on a nut in a tight space. You can flip the wrench over and get a new bite with only a 30-degree swing arc.
Clever. Box-end wrenches. They surround the nut.
Exactly, hence the name box. They grip the fastener on multiple points, usually 12 points inside.
Why 12 points, not 6?
The 12 points mean you only need to swing the wrench 30 degrees to get a new grip, or 15 degrees if you flip it, which is great in confined spaces. They give excellent grip for breaking loose tight nuts or applying final torque.
But maybe slower for just spinning a loose nut off.
Can be, yeah, if you can't turn it continuously. Which leads us nicely to
Combination wrenches.
the best of both worlds. Box end on one side, open end of the same size on the other.
So you use the box end for the heavy work,
Yeah.
breaking it loose, or final tightening.
Exactly. And then flip to the open end to spin it off or on much faster. Very efficient.
And ratcheting box end wrenches speed things up even more.
They do. Allow you to swing the handle back and forth without taking the wrench off the fastener. Very useful.
Okay, socket wrenches. These seem like a system.
They really are. Two main parts. The socket, which fits over the nut or bolt, and the handle that attaches to the socket.
Lots of handle types.
Oh, yeah. T-handles, ratchet handles, screwdriver grips, speed handles for rapid spinning, breaker bars for high torque, plus extensions of various lengths, universal joints for awkward angles.
The sockets usually come in sets with detachable handles.
Most commonly, yeah. The handle has a square drive lug, 1/4 inch, 3/8, 1/2 inch are common sizes that fits into a square recess in the socket.
And there's usually a little ball bearing.
A spring-loaded detent ball, yeah. It clicks into a recess in the socket wall to hold it onto the drive securely.
What about the adjustable wrench? The classic crescent wrench.
A very versatile utility tool, no doubt. Smooth jaws, adjusted with a thumb screw or worm gear. That opening is usually at a 22.5-degree angle to the handle.
But not a replacement for standard wrenches in aviation.
Generally, no. They can slip more easily if not perfectly adjusted, and they don't provide the same precise grip as a fixed-size wrench. Always adjust them snugly onto the fastener.
And a key usage tip.
Always pull, so the force is on the fixed jaw, not the adjustable jaw. Pulling on the adjustable jaw side increases the chance of it slipping or breaking.
Good to know. Okay, then we get into special wrenches. Things like crowfoot wrenches.
Exactly. These are like open-end wrench heads without a handle designed to fit onto a standard socket wrench handle or extension. They're for reaching fasteners, usually on tubing or in tight spots where a normal wrench or socket won't fit.
And flare nut wrenches. They look like a box end with a slot cut out.
That's a good description. They're specifically for the B-nuts used on fluid lines, fuel, hydraulic, oxygen lines. The opening lets them slip over the tube, but they provide much better grip on the soft brass or aluminum fittings than an open-end wrench, preventing damage.
And both crowfoot and flare nut wrenches can often be used with a torque wrench.
Yes, they usually have that square drive receptacle, which is a major advantage for ensuring proper torque on critical fittings in hard-to-reach places.
Then spanner wrenches for round nuts.
Right, nuts with notches or holes on their periphery or face. There are several types. Hook spanners curve around the edge. U-shaped hook spanners engage face notches. End spanners are like sockets with lugs. Pin spanners use pins for edge holes. Face pin spanners use pins for face holes.
Depends on the type of nut you're dealing with. And Allen wrenches.
Or hex keys. L-shaped or straight hex bars used for internal wrenching hex socket screws and bolts. Very common. Sizes from tiny fractions up to 1/2 inch or more.
Now, the torque wrench. Hugely important.
Absolutely critical. It's not just a wrench, it's a precision measuring instrument for applying a specific predetermined amount of rotational force or torque to a fastener.
Needs careful handling and calibration.
Definitely. Visual inspection before each use for any damage. And they require periodic calibration, could be 6 months, 12 months, depends on use and manufacturer guidance to ensure they remain accurate. Accuracy is paramount.
Common types. Deflecting beam, dial indicating.
Those are two main visual types. Deflecting beam, you watch a pointer move along a scale. Dial indicating has a gauge like a clock face.
And the clicker type.
Micrometer setting type. You dial in the desired torque value, and when you reach it, the wrench gives a distinct click or impulse you can feel and hear. Very common now.
Lastly, in wrenches.
Yeah.
Strap wrenches and impact drivers.
Strap wrenches are fantastic for gripping round or irregular shapes, especially delicate components like tubing or polished fittings without scratching or crushing them. They use a fabric or rubber strap.
And impact drivers. Used with a hammer.
Yes. You strike the end with a hammer or mallet, and an internal cam mechanism converts that impact into a powerful rotational force. Excellent for loosening really stubborn or corroded fasteners that won't budge with a normal wrench. Need special impact-rated bits and sockets, though.
Phew. And a lot of wrenches. Okay, let's switch to metal cutting tools. Hand snips first, like scissors for sheet metal.
Pretty much. You have straight snips for straight lines and outside curves, curved or hawksbill snips for inside curves or circles, and then aviation snips.
Aviation snips sound heavy-duty.
They are. Designed specifically for cutting harder materials like heat-treated aluminum alloys and stainless steel, which are common in aircraft. They often have compound leverage handles, making it easier to cut thicker sheets, maybe up to around 50 thousandths of an inch.
And they come in left and right cutting versions.
Yes, refers to which side of the blade the waste material curls away from, allowing you to cut tighter curves in that direction. Yellow handles usually mean straight cut, red for left curves, green for right curves.
Important note, don't use them on too heavy metal.
Correct. You'll damage the snips or just won't be able to cut it. And remember, snips shear the metal. They don't remove material like a saw.
Which can cause tiny fractures.
Sometimes right at the edge. So a good practice is to cut slightly outside your line, maybe 132nd of an inch, and then finish the edge smooth with a file.
Good tip. Now, hacksaws. Blade, frame, handle.
The basics. Crucially, the teeth must point forward, away from the handle. Cutting happens on the push stroke.
Blades come in different materials and types.
High-grade steel, sometimes tungsten steel. All hard blades are brittle, but cut tough materials well. Flexible blades have only the teeth hardened, better for thin or hollow sections where an all-hard blade might snap.
And pitch teeth per inch matters a lot.
Absolutely. Coarser pitch, fewer teeth, like 14 TPI, for thick, soft materials. Finer pitch, more teeth, like 24 or 32 TPI, for thinner or harder materials. The rule of thumb is to have at least 2 or 3 teeth in contact with the material at all times.
Using a hacksaw properly involves
selecting the right blade, mounting it correctly with proper tension, not too tight, not too loose, securing the work firmly in a vise.
nicking the start point helps.
Yes, with a file edge. Prevents the blade jumping around when you start. Hold the saw firmly. Start the cut just outside the line with light pressure. Use steady, even strokes, using a full length of the blade.
Pressure on the forward stroke only.
Yes. Lift slightly or relieve pressure on the back stroke. Aim for maybe 40-50 strokes per minute. Don't force it. Let the blade do the work.
And clean up and loosen the blade after.
Good practice. Relieves stress on the frame, protects the blade.
Okay, chisels. For cutting metal softer than the chisel itself.
Right. Used for shearing off rivet heads, splitting stubborn nuts, cutting in tight spots, usually made of hardened and tempered tool steel.
The cutting edge is slightly convex.
Yeah, helps absorb shock and prevents the corners digging in too sharply. A general cutting angle is around 60-70 degrees. Hold it firmly. Strike squarely with a ball peen hammer.
Types include flat cold chisel,
Your basic general-purpose chisel.
cape chisel,
Narrower blade for cutting grooves or square corners.
round nose chisel,
For semicircular grooves, or sometimes used to help recenter a drill that's gone off track.
and diamond point.
Square point ground sharp, good for V-grooves, or cleaning out sharp internal corners.
Right. Files. So many shapes and sizes.
An incredible variety, made from hardened tool steel, known by their cross-section, overall shape, or intended use. The cut is also key.
Cut meaning the teeth.
Yes, how coarse they are rough. Coarse, bastard, second cut, smooth, dead smooth, and the pattern, single cut or double cut.
Single cut has 1 row of teeth. Double cut has 2 rows crossing.
Exactly. Single cut gives a smoother finish, good for sharpening or soft metals. Double cut removes material faster, but leaves a rougher surface, good for general shaping.
Proper care is vital. Keep them clean, dry, separated.
Absolutely. Rust dulls them. Banging together damages teeth. Use a file card that wire brush to clean out filings, brushing along the direction of the teeth. A clogged file doesn't cut well and can scratch the work.
Some common types. Hand files have a safe edge.
Often, yes. One edge without teeth, so you can file up against a shoulder without damaging it. Usually double cut.
Flat files are the most common.
Probably. Tapered slightly, double cut sides, single cut edges. General workhorse.
For mill files, single cut.
Usually. Good for draw filing, lathe work, finishing soft metals.
Square, round, or rat tail, triangular, 3 square, half round.
All named for their cross-section. Used for specific shaped slots, holes, corners, curves.
And specialized ones like lead float, warding, knife, wood, fixin' files.
Yeah, for soft metals, narrow slots, acute angles, wood, and rapid finishing on soft materials, respectively. Vixen files have curved teeth, quite distinctive.
Filing techniques. Cross-filing and draw filing.
Cross-filing is the standard method, pushing the file forward and slightly sideways. Draw filing involves holding the file at both ends and pushing it sideways across the work gives a smoother finish. Pressure on the forward stroke only in both cases.
And removing burrs is important.
Critical for safety and proper fit of parts.
Lathe filing.
Using a file, often a mill file or long-angle lathe file, against a rotating workpiece in a lathe, requires care and specific technique.
And that's files covered. Let's talk drills. Hand drills, power drills.
Hand drill or egg beater for small holes. Breast drill for larger holes using body weight. Electric and pneumatic power drills are most common now.
Pneumatic preferred around flammable materials.
Yes, because they don't create sparks like electric motors can. Safety first.
The bits are usually twist drills.
Overwhelmingly. Cylindrical hardened steel, spiral flutes, conical cutting point.
Material matters. Carbon steel versus high-speed steel. HSS.
Carbon steel is okay for softer stuff, but HSS is much better for metals, especially tougher alloys like stainless steel. It stays harder at high temperatures.
Most have 2 flutes.
Yes. Helps clear chips and allows coolant in. 3 or 4 flute drills are usually for enlarging existing holes.
Key parts. Shank, body, point.
Shank fits in the chuck. Body has the flutes, margin, clearance. Point has the cutting lips, chisel edge, and crucial lip clearance angle.
Standard lip angle is 118 degrees.
For general metal drilling, yes, 59 degrees each side of the axis. Softer materials might use a sharper angle. Harder materials, sometimes a flatter angle.
Shank types vary too. Straight, square, tapered.
Straight for most hand and power drills. Square for old-style braces. Tapered for larger drill presses.
Sizes are fractional, letter, number.
All 3 systems are used, and you often need conversion charts to see equivalents, from tiny number 80 up to large fractions.
Sharpening is key.
Essential. A dull drill cuts poorly, overheats, makes oversized or rough holes, needs the correct point angle and lip clearance. Can be done by hand on a grinder, but jigs or specialized grinders give better results.
Okay, after drilling, sometimes you need a reamer.
Yes, if you need a hole that's very smooth, perfectly round, and extremely precise in size, reamers enlarge a pre-drilled hole by just a tiny amount.
How much undersized should the hole be drilled?
Only a few thousandths. Typically 0.0003 to 0.007. Removing more will overload the reamer.
Made from tool steel or HSS like drills?
Yes. And they're quite brittle, especially the cutting edges, so handle with care.
Critical usage rule.
Rotate only in the cutting direction, usually clockwise. Never turn it backwards in the hole that dulls the blades and can score the hole. Turn smoothly and evenly.
Types include straight and spiral fluted.
Straights are common. Spiral fluted tend to cut more smoothly, less chatter, better for interrupted cuts like keyways. Both usually have a slight taper at the start.
Bottoming reamers for blind holes. Expansion reamers are adjustable.
Correct. And taper reamers for creating precisely tapered holes.
Next, countersinks.
Yeah.
For making holes except flush fasteners.
Exactly. Cuts that cone-shaped recess so the head of a countersunk screw or rivet sits flush with the surface. The angle has to match the fastener head.
100 degrees is standard in aviation.
Very common, yes. You also see 82 degrees sometimes.
Stop countersinks allow precise depth control.
Yes, often with micrometer adjustment. Crucial because you don't want to remove too much material, which weakens the joint.
Right. And finally for cutting. Taps and dies for threading.
Tap cuts internal threads, like in a nut. Die cuts external threads, like on a bolt. Hardened, tempered steel. Very precise.
Standard thread types. NC, NF, NEF, NPT.
National coarse, fine, extra fine, and national pipe taper. You need the right tap or die for the specific thread required.
Hand taps often come in sets of 3.
Taper, plug, and bottoming. Taper starts the thread easily, plug cuts threads further down. Bottoming cuts full threads right to the bottom of a blind hole.
Dies are for external threads. Adjustable or plain.
Yes. Adjustable round split dies allow slight size adjustment. Plain ones are fixed, held in a die stock handle for turning. Taps are held in tap wrenches.
Okay, great overview of cutting tools. Last section, layout and measuring tools. Precision is everything here.
Absolutely. These tools determine the accuracy of the final work. Handle them carefully. Dropping them can ruin their precision.
Starting with basic rules. Steel, rigid, or flexible.
Usually steel, graduated in fractions of an inch down to 64 or decimal inches, hundredths. Used for measuring or as a straight edge.
Combination sets sound very useful. Square head, protractor head, center head.
Incredibly versatile. The square head with the blade acts as a tri-square, depth gauge, height gauge, marking gauge, 45 and 90 degrees. Has a built-in level and scriber.
Protractor head for angles. Center head for finding the center of round stock.
Exactly. A whole layout toolkit based around one accurate blade.
Scribers are for marking metal. Sharp points.
Like a hard steel pencil. One point often bent for access. Keep points sharp. Use with the straight edge. Make lines just visible enough, not deep scratches.
Only for lines to be cut, because they create stress points.
That's the general rule, yes. Avoid scribing on areas that won't be removed if possible.
Dividers and pencil compasses for arcs and circles.
Dividers have 2 steel points, good for transferring measurements accurately or scribing circles to be cut. Pencil compasses have one point and a pencil lead holder, better for drawing on surfaces you don't want to scratch.
Set them using a rule. Sharp points are key.
Yes. Place one point on a roll mark, adjust the other leg to the dimension, then swing the arc or circle, tilting slightly in the direction of rotation.
Calipers next. Inside-outside, hermaphrodite.
Basic comparison or rough measurement tools. Outside calipers measure diameters or thicknesses. Inside calipers measure hole diameters or slot widths. Hermaphrodite calipers, one pointed leg, one curved, are mainly for layout, scribing lines parallel to an edge.
But for real precision, we need micrometer calipers.
Yes. Outside, inside, depth, and thread micrometers. Standard sizes like 0.1 inch, 1/2 inch, etc. Measure to thousandths, even 10,000ths of an inch. Digital versions are also common now.
Outside mics are most used by AMTs.
Probably. Shaft diameters, sheet thickness, checking drill sizes. Lots of uses. Reading them takes practice, but is systematic.
You read the barrel scale, tenths and .025 marks, and add the thimble scale, .001 mark.
It's the basic process. Barrel shows the main increments, thimble refines it to the thousandths.
Some have a vernier scale for even finer readings.
Yes, allows reading to 10,000ths, .00001. You see which vernier line aligns perfectly with a thimble line.
Careful handling is essential. Use the ratchet stop. Calibrate regularly.
All crucial for maintaining accuracy. They are precision instruments.
Dial indicators are related. Measure surface variations.
Sort of. A probe contacts the surface, and its tiny movements are amplified and shown on a dial, or LCD, used for checking things like shaft runout, bend, or surface flatness, like on a brake disc. Needs to be mounted rigidly.
And finally, slide calipers, like vernier calipers.
Yes. More accurate than a rule, easier to use than a micrometer for some things. Jaws for inside-outside measurements, often a depth rod too. Read from the main scale plus a vernier scale or a digital display.
Wow. That covers an incredible range of essential tools. It really drives home the precision and care involved in aircraft maintenance.
It absolutely does. Every one of these tools, used correctly, plays a part in ensuring an aircraft is safe and reliable. Understanding them is fundamental.
From the simplest hammer or file to a precision micrometer, it's all about selecting the right tool, using it properly, and taking care of it.
Exactly. It's a combination of knowledge, skill, and discipline.
And it makes you think, doesn't it? Every time you see a plane, remember that its safety relies on countless small actions, performed correctly, using tools just like these. What other complex systems depend so fundamentally on such seemingly basic yet critical elements?
That's a great thought to end on. The hidden foundations of complex technology.